Yes, thank you, Marek, and thank you very much for the invitation to this very interesting workshop. It is really a pity that we cannot be there in person and meet friends and discuss more thoroughly all this fantastic new data that experimentalists are offering us. So the title of my talk is about multi-quark states, obviously, and I would like to offer a somewhat different of an orthodox point of view about these states, accompanied, given my history in this field, accompanied by some historical observation about experiments and theory. So the initial paper was in 1977. Remember this date because that was the year in which the Jaffe papers appeared, after which infinitely many other theoretical and experimental papers were published on the subject of multi-quark states. Of course, this list is only to give you an idea how many people, how good people have entered the field. Now, what I would like to discuss with you in the short time that has remained to me, some bit of history or prehistory, and present you a unified QTD description of color singlet quark states capable of encompassing ordinary mesons and baryons, as well as multi-quark states, especially what I would like to call baryonic states, namely states with hidden baryon number. Then, if I have time, I don't know, we'll see, I may have some phenomenological consideration about exotics, the penta-quark PC photoproduction, and I would like to present you a crude mass formula for multi-quark states and a few conclusions. So a bit of praise. Everything started in 1974 with the discovery of a bump in p-bar P and p-bar deuterium experiments. This was called S9030, you may remember. And this state was confirmed in a number of other experiments like Shalukka et al., Bruckner, Sakamoto. But then at the end, a very high statistics investigation was carried out at BNL, and this state was not found. It was not even found clear, so this bump completely disappeared, although it was very narrow, something like 2 to 4 MeV. But today we have this activity around the pp bar threshold, which is sketched here. There may be is a shadow of this state. We don't know. Okay, but the interesting situation is that there was a kind of a roller coaster for these multi-quark states. They appeared and disappeared in a very frustrating way until we had firmly confirmed the X3872, some Y and Z states, and more recently this TC3875, very interesting states, which I give you here, the experimental evidence that you certainly know very well. This is the experimental evidence for the penta-quark that was also shown in previous slides by other speakers. Why I present you this picture, this experimental data? Because this state has been confirmed by the same group in this paper in 2016. But as far as I understand, and Shepard gave me this information, this state was not confirmed in GluX experiment, photoproduction, namely in photoproduction. This is a very worrisome situation that should be clarified. pretty soon, hopefully. One has to say that the photon energy is barely capable of producing the PC, the penta-quark. So I don't know if there are experimental problems. I don't know. We still have to see. Okay, so let me go to the theoretical part of my talk. I want to show you that this unified picture of hadrons emerges from color string. Color string is very appropriate for this workshop, plus planarity. And you immediately see that you have to have meson baryons at the same level as multi-quark states, especially those states that have hidden baryon number. So the theoretical framework is as follows. As I said, multi-quark states emerge in a topological expansion of QCD. Topological, I mean an expansion where this state appear at the level of leading planar and dual amplitudes. Then there will be non-planar collections. Planarity, which means the dominance of planar diagrams, and planar duality was introduced and postulated by Rosner in 1968. And it's very interesting that this year was the year in which Veneziano published his fully planar dual amplitude. So the idea of planarity and dual planarity was around, sorry, not planarity, the idea of duality was around in those years. Now, we want to show that this notion can be extended to completely put on the same footing, and let me extend the notion of duality when baryons are present. So I will show you that how duality is implemented in meson baryon and baryon anti-baryon amplitudes. This last kind of amplitude required introducing the notion of junction for baryons. From the theoretical point of view, planarity can be seen to emerge not only in a number of large N expansions like NC at fixed Toft coupling, or the so-called, technically called topological expansion introduced by Veneziano, but also as well as from lattice results, as I will show you in a moment. By the way, adding duality, as suggested by Rosner, then necessarily Y-shaped baryons and multi-quark state of the baryon type emerge. In our last paper, we have proved that rigorously at large Toft coupling, which in a regularized lattice description of QCD is equivalent to a large G-square expansion, minimal area diagrams dominate scattering amplitude, which means, if you think a second, this means planarity. So in the large Toft limit, planarity, planar diagrams, in a sense that I should also make clear in the case when baryons are present, dominate the amplitudes. Then, from the point of view of lattice data, there is this very nice simulations. I show you this little movie. Sorry, you see that we have 3 color charges. If you let them go apart, in the flux, the Y-shaped flux among these 3 quarks emerges very, very clearly. So the baryon as a sort of Y-shaped picture, and you can understand why. The reason is as follows. Well, the lowest building blocks for all these mesonic and baryonic amplitudes are as follows. You have the meson Q bar Wilson line Q representation of the meson. When the meson propagates, you span this surface. But the baryon is more complicated. You have to have three strings, three Wilson lines that meet to a point. This point is what we will be calling junction. When the baryon propagate, this junction flow. And what is interesting is that at the level of the planar dominance, this point here, this point, always lies at the minimal distance from the quarks.
Giancarlo, we are past 15 minutes.
Okay, thank you. Well, so then you see what happens for the amplitude. In lattice regularization, planarity is the leading topology, and amplitude span surface of minimal area. Corrections are depressed by the Toft coupling. And you see, this is the meson propagation, this is the global, this is the baryon, and you see why it's planar, because the leading term in this limit is the one in which these are kind of sheets covered by plaquettes. This is like a book with the planar sheets and sewed along the junction. At this point, you can compute meson amplitude. They are obviously dual. S-channel mesons are dual to T-channel mesons. And the decay and the interaction occurs via string breaking, string fusion. If you have baryons, you have to keep in mind that there is this junction. This junction has to be drawn in this to give the correct topological shape of this amplitude. Here again, the dynamics proceeds via string breaking and fusion, and you see that, of course, this is a standard decay of a baryon. Now, in this case, baryons are dual to mesons. But something new and interesting occurs if you try to construct BB bar amplitude. In this case, you have a number of ways to glue together two baryonic propagators. And they are, in the case of tricolor, they are drawn here. You see, this is a plane. These are two planes sew along these two dotted lines. These are three planes sewed along the dotted line. Now, immediately you recognize the new intermediate S-channel necessarily emerge. Here they are. You see that in this amplitude, the intermediate states in the S-channel is a tetra-quark. Then you have other kind of mesons. But let's focus here. Now, of course, what can happen is something else dynamically. So you have to imagine that this is the flow of junction, that is to say, is the flow of the baryon number from the initial to the final state. And of course, the baryon number can annihilate, and then you get what are called BB baryon annihilation diagrams. Sorry. And they are, you see, they are here. This one, this diagram has exactly the same flavor as the scattering one, in which the junction was running horizontally, but now the junction is closed in the initial state and created in the final state. And you see the topology. The topology is, this is a plane. These are two planes sew along these two lines. So the intermediate states now is in the S channel you have two QQ bar jet, and in the T channel you have this funny meson. That if you insert, obviously, if you insert the loops, this meson decays into baryon anti-baryon. Now, let me just stress that the meson decay mesonic decay of a tetra-quark is very complicated dynamically, because you have to annihilate this line to a point, and then by a color arrangement you have two separate mesons. So we have the idea, and we conjecture that this complicated rearranging, junction annihilation and color rearrangement is somewhat dynamically disfavored. It's like the violation of the Zweig rule, where now the role of flavor is played by the junction.
Giancarlo, we are 20 minutes.
But how much do I have?
Another 10, and then we need another 10 for discussion.
Okay, thank you for recalling me. So I compare here for you two amplitudes that have exactly the same flavor structure. The blue lines are identical, but the green line run in a different way. So this is the scattering amplitude, this is annihilation. And to identify what is the structure of the amplitude, you need to tell me how the junction runs through the diagram. When I say junction, you have to read the Baryon number. So the Baryon number here goes from initial to final. Here the Baryon number is annihilated in the initial state, is recreated in the final one. And this is two sheets, this is one sheet. Now, another point, so at the level of planarity, Tetra-quarks are necessarily present. You can also see this as a need to implement unitarity in planar diagrams. This is shown here. This figure is taken from our physics report in 1980, where we show that if you want to account for extended generative violation of strange ranging trajectories, you have to assume that in the U channel you have a penta-quark, while in this other amplitude, necessarily at the same level of approximation, you have to have a tetra-quark. At those times, the tetra-quarks were called M4J in the T channel. So they are penta-quark, tetra-quark are on the same footing with, from the point of view of unitarity, when unitarity is imposed at the planar level. We also, on those old papers, made the point, this picture is taken from the paper, that there were very many other possible weird states like the ones that I've drawn for you here. In particular, for the first time, we conjectured that there was a penta-quark besides a state with two quarks and two anti-quarks that was also conjectured by Rosner. So the main conjecture that we can draw from this situation is as follows. Fully baryonic decay that occurs via string breaking is dynamically favored with respect to the mesonic decay where string annihilation and color arrangement is necessary. Of course, this is a very wild conjecture. I agree with you. There is no real dynamical calculation behind, but it gives you something good, namely, if kinematics forbids it, the baryon state can be, tetra-quarks can be unusually narrow. That is to say, if the BB bar threshold is above the mass of the tetra-quark, the tetra-quark may be narrow because it doesn't like to decay into mesons. Of course, this is not the only interpretation. I mean, there is a lot of the literature, alternative interpretations that I'm not going to discuss here, and you know better than me what they are. Now, of course, the point of this conjecture, the weak point of this conjecture is as follows. What we proved that at large Toft coupling, the description I give you is rigorously true. But of course, we are not, this is not QCD. We are here. We are here. No, sorry, we are here. We are here. Strong coupling or large and in such a way that where you have a G square and C large. but physics, real QCD is there. And the question is, can you go from here to there without losing all the nice properties I have described to you? I don't know. I have to say, I cannot tell. Certainly, in the large Toft limit, the penta-quarks, tetra-quarks, they necessarily appear exactly like mesons and baryons appear in the theory.
You have
There's
5
nothing
minutes
special about
left.
it. Okay, so let me go then quickly. This was the P5 description of photoproduction, discussion of photoproduction, because we have this problem that maybe is not confirmed, so I skip this. Instead, I want to propose you a very simple formula for narrow baryon state, which is as follows. We deny to supposedly dynamically dominant hadronic string breaking, decay mode of baryon states, we are led to conjecture some oversimplified mass formula, namely the mass of a tetra-quark plus this extra energy is equal to the mass of the baryons. So if this is, in case this mass is below the mass of the two baryons. Similarly, for the penta-quarks, you have to add 2 of these bits because you need to break 2 strings to end up with baryon, anti-baryon, baryon. Now, so delta HSB is the bit of energy that one needs to provide to let the multi-quark state decay into baryons by string breaking. We expect that this is the order of some QCD scale and somewhat universal if this has to have any use. Of course, this is a very crude formula, nothing to do with the extremely well-founded and refined formula that, for instance, Caroline and Rosner have elaborated. But this is a few applications. You see, for TCC, X3872, YB 10088, and the penta-quark. And you see that if you apply this rule, extremely simple rule, you get that this delta is around 700 MeV. Here you have 1400 because this represents twice this delta. So delta from this data comes out to be 700 MeV, which is so we interpret it as what we need to create a QQ bar pair and a QCD string bit, something that looks very much like the meson that incidentally has a mass of 770 MeV. So this sort of fit with these numbers. But of course, I cannot hide that if you consider not so narrow state, that this is not working anymore. I mean, at least not so nicely as in the previous cases. And these are a few examples. So the delta, if I estimate according to my rule, ranges from 940 to 350 almost. So nevertheless, let me compare this formula, the formula applied to the still to be found BB U bar D bar state. Let me compare the mass estimate given by Caroline and Rosner, which is summarized here, with the one that we might propose. Of course, our formula is much weaker because we don't know neither the mass of the tetra-quark nor the mass of the BBU baryon. But at least we can establish a relation within the mass of the tetra-quark and the mass of the baryon, which is written here. So we expected BBU bar D bar to be mass of the, when we will be found, this baryon plus more or less 250 MeV. Okay, so now I come to my conclusions. Starting from the planar approximation, so if a systematic expansion of QCD is constructed, which provides a unified picture of hadrons where a new family of necessarily exotic, possibly exotic multi-quark hadrons emerge based on the notion of junction or flow of baryon number, something which lattice data do confirm. Then you have in the spectrum, in this approximation, Tetra-quarks with 0 baryon number and junction-anti-junction structure, penta-quarks with baryon number 1 and junction-anti-junction junctions structure, and the baryons with this funny structure. We conjecture that the dynamical Kavli state is by string breaking as opposed to J junction-anti-junction annihilation in color arrangement, which would correspond to a kind of junction-Zweig rule violation. The nice thing about this conjecture is that if kinematically forbidden, the baryonium baryonium state can be unusually narrow, because they would like to decay into baryon-antibarion, but there is not enough phase space, or there is no phase space available. This can be contrasted with the X4730 state, which instead is above the lambda plus lambda minus C threshold, and in fact it is quite wide, it's under the ADMEP. I didn't discuss photo reduction, and I tried to give you a crude formula for narrow baryon states, which at least for narrow states it seems to work, as giving some sort of support to the picture that the leading decay mode for those states is by string breaking. When I say string, I mean QCD string, of course, not the 10-dimensional string. Okay, now most probably, however, when you switch on and when you consider all the non-planar corrections, the multi-quark states that we are experimentally finding will be superposition of with different weights of different kind of descriptions, like d-quark, anti-d-quark bound states, molecular d-meson configuration, and so on and so forth. Okay, I think I will end here, and I'm sorry for the difficulty I had in having the slide to smoothly run, and let me thank you for your kind attention.
So thank you very much, Giancarlo. The floor is open for discussion. Arkady.
Okay, Giancarlo, thank you for the talk. And I mean, okay, I still remember all times and particular stuff. I'm not sure whether it's related to your ideas or not, but I learned it from Alexei Kaidalov at some point about it was about normal, you know, kind of rigid trajectories for baryon and mesons, and there it was some kind of, I don't know, he called it like supersymmetry, that was kind of analog structure of you know, this corresponding resonances with some shift between baryon and meson. It was not about exotic stuff, but I wonder whether it's related to your ideas.
Okay, in the old times we had a section of our work on range trajectory, because at those times these were, you know, sort of fashionable. They are not anymore, but yes, you can try to put these states on range trajectories and give try to sort of fit slopes and intercepts. I mean, the picture that you get is quite complicated, because you have to understand that these states, I didn't have the time to go into this, do mix with ordinary baryon and mesons, especially.
No, but it was some kind of conspiracy between Baryonic and Mesonic trajectories not related to exotics, just for normal one. And I'm recollecting this one, and I think that you could be involved with this as well.
Well, then, when you say conspiracy or Baryonic trajectories, I mean, and Mesonic are Mesonic, so this does not identify whether you are talking about, at least I didn't understand, whether you are talking about penta-quarks or
not penta-quarks.
Tetra-quarks or mesons.
No, it's a normal 3-quark baryon and.
Okay.
Yeah.
Okay, thank you. We have to move on. We have little time. Kobe, you had a question.
Yeah, I would like to ask you whether in your picture the baryon is a Y-shaped a junction with a Y-shaped strings or a diquark with a single string and a quark on the other side. It seems from the simulation and from the diagrams that you have in mind a Y-shape, but I want to say that from experiment we know that the picture is of a diquark and a quark and not Y-shape, because if you look on the radial trajectories of baryons, they have the same slope up to 5% as the radial trajectories of mesons. Had it been a Y-shape, it should have been 2/3. So it's clearly excluded by experiment. And by the way, there is also a theoretical works by Sharov and by Truth, where they show that if you start with the Y-shape and you introduce some small fluctuation, shorten one of the arms, it's unstable and it will decay into a diquark, quark, and string between them. So I think that the right picture to describe baryons is not a Y-shape. Thank you.
However, what I was showing is the lattice simulation that cannot be doubted. Maybe the point is that what I'm describing applies at the level of the planar amplitudes, and it may well be that when you take into account all possible correction, this picture is not adequate anymore. So I guess this is the interpretation of these results, if I understand. Unfortunately, I was not familiar with these papers.
Giancarlo, these lattice simulations have been done with infinitely heavy quarks, which are static, and then you look for minimal flux configuration. But in real world, quarks, at least some of the quarks, are much lighter than lambda QCD.
I know.
So the situation, I think, is likely to be much more complex. But anyway, the next question is from Volodya, I think.
Yeah. Thank you for the nice talk. I would like to ask about one over the perspective of 1/n expansion for baryons. Baryons in the planar limit consist of infinitely many quarks, and we have some formulations for this situation, like Witten's mean field approach, or even once with Sasha Migdal we wrote loop equations a la McCain-Migdal for the baryon, realizing this picture. But do you think the fact that we are so far from n = 3 in this picture destroys all hopes for efficient planar approximation description of baryon? Do you have some maybe data or considerations in this respect?
Strictly speaking, our theorem applies in the large Toft limit, which does not necessarily mean NC very large. It could be G² large. So if you were on the lattice, you use the lattice regularization of QCD, then you would like at fixed NC to call this a large, a strong coupling expansion of the theory. So you can very well live with NC small or fixed and let G² go.
But then we will be on the wrong side of the phase transition, yes?
I agree. That's I was already. That's why I had this slide. Okay.
Oh, thank you. I think I just have one quick comment about
Thank you.
the absence of penta-quark signal in photoproduction.
Okay, very good.
There is a very strong indication from explicit calculations in a molecular model by Ding-Song Zhou and collaborators that the branching fraction in the decay of the pentaquark into J psi and proton is much smaller than into a charm baryon and an anti-charm meson. So that could be the reason why. What this means is that the effective coupling to the pentaquark is very small.
But then, but why this would prevent this decay? Okay, so you are telling me that this is not the right one, final state to look at, but perhaps this one. Or...
Exactly, that's exactly what I'm saying, but it's much more difficult experimentally.
But I'm afraid that they have to increase the photon energy because this final state is a bit too heavy to be produced.
No. The lambda CD, I think, is still okay. And I can send you later perhaps a reference, but okay, we really have to move on to the next talk.
Okay.
So thank you very much, Giancarlo, and
thanks for the nice atmosphere you have been able to, create.
Thank you.